Okay, so we should be recording. And this is a good one because it actually incorporates all of the different ways to do stoichiometry. That is gas and solution and mass. So it'll be a good example for you. If you can kind of understand this one, then you'll be in good shape for all the rest. So it starts with a solution. So we've got acetic acid. There we are. Uh, Hold on. Well, not going to work if we can't get that done. Hold on. There we go. We've got acetic acid and we've got a concentration there, so we know we can convert to moles there. And we've got a mass of magnesium, so we know we can convert to moles there based on the molecular mass. And then we're going to ultimately have to figure out what the volume of hydrogen gas is that we're producing. And so the first thing we've got to do is come up with the chemical equation. And for this, again, you've got to remember what uh, the ions are. So we've got acetic acid, which is acetate. And when we make it an acid, we just put a hydrogen in front of it. So acetate is C2H3O2. Okay. And it reacts with magnesium. And this is aqueous. And this is solid. And it produces, in this case, we can see since it tells us it's hydrogen gas, it's going to be H2. We have to remember that that's a diatomic. And then the only other thing that can happen here is that magnesium can kick out the H, and so it combines now with the acetate. But we also have to remember that magnesium is a 2 plus ion. So that means, and acetate is just a 1 minus ion. So that means we're going to need two acetates to make this molecule neutral. And that's also going to be aqueous now. Okay. So now we got to check for our balancing. And if we just look at that acetate, now we've got two. So we know we're going to have a two over here. And as it turns out, that balances it nicely because those two H's then go there to the gas. Okay. So now we've got a balanced equation. That's the first step. And now we've got to figure out, notice it tells us we've got a certain quantity of acetic acid and a certain quantity of magnesium. So that means we're going to have to handle this as a limiting reaction or limiting reactant problem, which means we've got to just do the stoichiometry twice. I mean, it's not a different system. It's just a different process. It's just a matter of doing the process twice. So first, let's figure out how many moles of hydrogen gas we can get from the acetic acid that we're starting with. And in order to do that, we have to figure out how many moles of acetic acid we're starting with. And so we're starting with 50 0.0 mLs. I'm going to go ahead and convert that to liters because we know molarity is in liters. So we have 0.05 liters of acetic acid. I'll just say acetic acid. And we have to use the conversion factor of the molarity, which it's just 6.0 moles over 1 liter. Okay. So that's remember, anytime you see a molarity, think of it as a conversion factor. And now we can actually go ahead and go straight to hydrogen because we can use our molar ratio. And we see that we get 1 mole, this is acetic acid, we get 1 mole of H2 for every 2 moles of acetic acid. This is the acetic acid. Okay. So now that can tell us how many moles of H2 we're going to get based on this. And let me calculate that. So it's 0.05 times 6 divided by 2 equals 0.15. And we've got just two significant figures because there's our two significant figures there. So that's moles of H2. Okay, does that make sense? So that's how much we could make if we used up all our acetic acid, but now we got to see if we have enough magnesium to use it up. And so we have to start with our 1.55 grams of magnesium, and we have to multiply that times the molecular mass, which we just get off the periodic table as 22.31, call it that. We have to give grams on the bottom, so I'm sorry, 24.31. 24.31 grams of magnesium per 1 mole of magnesium. And then we have to, again, figure out how much hydrogen we can get out of that. And in this case, it's just 1 mole of hydrogen per 1 mole of magnesium. Okay. So if we just divide that 1.55 divided by 24.31, we get 0.064 moles. Okay. And now that means this is the limiting reactant because, again, we get less of it, less based on the amount of magnesium that we started with compared to the amount of acetic acid that we started with. And so now we know this is the number of moles of hydrogen that we can actually generate given our two reactants. And now we have to figure out what's the volume of that. So the good news is that in our ideal gas equation, PV equals nRT, what we're going to be solving for is N. So N is going to be equal to PV divided by RT. And, I'm sorry, we're not solving for N, we're solving for volume. We have N, so let me fix that. So we're solving for volume, so now we just have nRT divided by the pressure. Okay. And we just have to plug in our numbers. Let's check our units, though. It's not on here, but R is equal to 0.0821 atmospheres times liters over moles times Kelvin. Okay. So that's an atmosphere there. So we have to change our pressure to atmospheres. We just do that by dividing by 760. So this equals 0.951 atmospheres. Okay. And then our temperature, we've got to convert to Kelvin. So we just have to add 273 is 288. Okay. And now looks like we can plug everything in. So we have N is 0.064 moles. So we're good there. We've got the correct units. And we multiply that times our constant, 1. Again, that's atmosphere liters divided by moles Kelvin. And then our temperature, which we converted to Kelvin, is 288. And then we divide that by the pressure, which we have now in atmospheres. That's K there. And this is atmospheres. And so this now is going to equal 0.0821 times 0.064 divided by 0.951. We're saying now we have 1.6 liters. Again, we only have two significant figures of H2. So let me just check and see if that's what the answer key says. So this is homework 19, number 4. Yeah, they incorrectly only had 3 significant figures, but we can only have 2 because that was our molarity here that we started with. so 1.6 liters of hydrogen.